start recording now. Okay, now this is the second part. Now, second part here, we will be looking at the properties. Yeah. So there are how many properties of thermodynamics? Okay, you have temperature, you have pressure, you have specific volume, you have internal energy, you have enthalpy, and then you have entropy. These are the properties of thermodynamics. Okay. So the first one, okay, before that, okay, we have to look into the properties that is categorized as intensive properties and extensive properties. What are the intensive and extensive properties of thermodynamics? So the property is the characteristic of a system. The characteristic of the system is determined by looking at all the properties of thermodynamics. The characteristic means the behavior of the system itself, actually. Okay. Now, some of the properties are, for example, the pressure, the temperature, and the volume. Okay. Pressure, temperature, volume, okay, or specific volume. And then, of course, you have the internal energy, the enthalpy, and the entropy. So properties are considered to be either intensive or extensive properties. Okay, what are the intensive and extensive properties? Now, intensive properties, those that are independent of the mass of a system, okay, such as temperature, pressure, and density. That means properties that does not depend on mass, okay, of the system. That means in kg. So these are temperature, pressure, and density. So temperature doesn't depend on whether you are referring to a mass of 1 kg or a mass of 2 kg, okay, of the system. Pressure also as well. Okay, so these are considered as the intensive properties. So extensive properties are those whose values depend on the size or the extent of the system. Depends on the size of the system, so the mass and the size. Yeah. Specific properties, okay, in extensive properties per unit mass. All the extensive properties per unit mass, that means per unit kg, is considered as specific properties. Let's say specific volume is an example. Okay, specific volume, which is in meter cube per kg. So let's say, for example, you have a system with a mass m, volume, temperature, pressure, and density. Okay, so if let's say when you refer to mass, okay, when you split the system into half, the mass also will be splitted into half and half. Volume as well. But the temperature, pressure, and density does not, okay, does not dependent on whether you are referring to the full size or the half size of the system. Okay, so mass and volume, they are the intensive property. Temperature, pressure, density, they are the extensive properties. So this is an example of, okay, the intensive properties here and the extensive properties here. Okay, so these are the, okay, those that, okay, these are the extensive properties and these are the intensive properties. Okay, extensive, that is mass and volume, which has to depends on the size or the mass of the system. And then temperature, pressure, and density does not depend. Okay, does not depend, independent. Okay, so that is the intensive property and the extensive property. So these are the basic that you have to know, because when you do thermodynamics 2, these are the things that you have to already know. Okay. Now the next thing is about state and equilibrium. What is a state? And usually we call it as a state point. And what is equilibrium? Okay, it will be explained here. So thermodynamics deals with equilibrium states. That means the state of balance. Okay, equilibrium states or the state of balance. Now equilibrium means is a state of balance. Okay. Now in an equilibrium state, there are no unbalanced potentials or driving force within the system. Okay, there will be no unbalanced potentials or any driving force within the system when you say the word equilibrium. Now, thermal equilibrium. What is thermal equilibrium? Thermal equilibrium can only be achieved, let's say, for example, in a room. Let's say at each corner of the room, you pick up a particle. Let's say, for example, you pick up a quantity of air and you start measuring it. Let's say the north, east, south, west. Okay, you pick up A from there, and then you measure at each corner. If let's say, for example, the temperatures are different between each corner, the temperatures are different, then we cannot say that the system is under thermal equilibrium, unless if the temperature that you measure at each corner within the room, if the temperature is the same, then we say the system, that is the air, is under thermal equilibrium. Then the next thing, that is mechanical equilibrium, that refers to pressure. Just now we refers to temperature. Now we refers to pressure. So if the pressure is the same at each corner, okay, at each corner, if the pressure is the same, then we say the system is under mechanical equilibrium. Now, phase equilibrium, if a system involves two phases, for example, solid and liquid. Take, for example, solid and liquid. Let's say, for example, you have ice, okay, ice. Now, if the ice melts, it becomes water, okay, it becomes water. Now, what does phase equilibrium here means? If a system involves two phases, and when the mass of each phase reaches an equilibrium level and stays there. So if let's say, for example, initially you have 1 kg of ice. So when you supply heat, the ice will melt and it becomes water. So if 1 kg of ice remains as 1 kg of water, then we say the system is under phase equilibrium. So you have thermal equilibrium, mechanical, and phase equilibrium. Then the last one is the chemical equilibrium. So if the chemical composition of a system does not change with time, that is, no chemical reaction occurs. For example, you have steam, S-T-E-A-M. Steam mixed with liquid water. Okay, so if water mixed with steam, there will not be any chemical reactions. Okay, because both are H2O. So we say after mixture and before mixture, they are under chemical equilibrium. Okay, so these are the 4 equilibrium conditions that we are referring. So if each of these being met, that means if let's say the system achieves thermal equilibrium and it achieves mechanical equilibrium, phase equilibrium, and chemical equilibrium, then we say the system is under thermodynamics equilibrium. Thermodynamics equilibrium. So let's say, for example, we refer to this diagram here for thermal equilibrium. Let's say, for example, when you refer to this, now it consists of, within the system, it consists of different temperatures, 20, 23, 30, 35, 40, and 42. Okay, this is not thermal equilibrium. So once it achieves same temperature throughout, so there is no difference in temperature anymore. Okay, then we say it is thermal equilibrium. So we say the system now is under thermal equilibrium. Now, for example, now from this, you can see mass 2 kg, temperature 20, for example, volume of 1.5 meter cube. Okay, this is what we call a state point. This is what we call a state point. So it's defined by this amount of mass, this amount of temperature, and this amount of volume. So the first point is defined by these properties here. If let's say you supply heat or you remove heat, okay, either one of these properties here changes, it will undergo a change in state. So let's say mass 2 kg, temperature is still remaining at 20, but the volume has already changed to 2.5. So then only we can say that the system has undergone a change in, okay, volume, and it enters or it achieves state point 2. Okay, so a state point is when you look at temperature, volume, and temperature, any properties of thermodynamics that is within the system has reached its equilibrium state, then we define it as one state point. But then when you supply heat or you remove heat, you supply work or you remove work, okay, that system will undergo a changes. But after the changes, and if the volume, temperature, and mass achieve a new equilibrium state, then we can define this as another state point. So usually when a system undergo a change in state point from one to another, we call it as a process. Okay. Now, process means any change that a system undergoes from one equilibrium state to another. Okay, that is what is called process. So remember, process always consists of two state points. And if we draw a line or a dashed line or a solid line connecting one state point to another state point, that line is called a process path. Okay, remember, process consists of two state points. Now, the series of states through which a system passes during a process is called a path or a process path. Now, to describe a process completely, one should specify the initial and the final states. So, for each process, you must have an initial state point and a final state point. So, minimum, it means it must consist of two state points, and also you must define which is initial and which is final. And the path that it changes from its initial to final is called a process path. Okay. So this is called a process path. So when it changes from one state point to the next state point, so we call it as process path. And this whole thing here is called a process. Okay, property A against property B. It can be specific volume, pressure, volume, enthalpy, entropy, and so on. That is based on the properties of thermodynamics. Now, what's quasi-equilibrium then? So when a process proceeds in such a manner that the system remains infinitely, okay, close to an equilibrium state at all times. So when the properties of the thermodynamics undergoes a changes, that means after it has already undergone a process, and if each property within that state point or within the system is still with equilibrium conditions, then we say it is a quasi-equilibrium process. And what is quasi-equilibrium? Quasi-equilibrium can be viewed as a very slow process. So slow process, that means every time it changes and a very infinite amount. That means so that the system or the particles within the system have enough time to adapt to the changes, Let's say from point 1 to point 2. So if let's say enough time are given for the particles to undergo changes from one equilibrium to the next equilibrium, then we say is quasi-equilibrium. So if let's say, for example, the process, or let's say a piston and cylinder device, if the piston were to move rapidly forward, if the piston were to move rapidly or very fast forward, what is going to happen is there will be piling up of particles or molecules in front of the pistons, and the rest of the space here, let's say, for example, the particles are still quite far away from each other. But in front here, you have the piling up of molecules, which the molecules are very close to each other. That will create two different pressure regions. So the region that is in front of the piston usually will have higher temperature, higher pressure. But whereas, okay, the rest of the space here has lower pressure and temperature, because particles, they are still very far apart from each other, still arranged properly. But the particles in front of the pistons, they are all colliding with each other because of the piston moving very fast forward. So that will create, okay, two regions of high pressure and low pressure here. Lower pressure. So what happens is, then we say the process of this is not a quasi-equilibrium process. So it's a non-quasi-equilibrium process. But if let's say it's moving slowly forward, compressing the system here. So what happens is the particles, they will have enough time to redistribute themselves within the system. So therefore, we say the pressure, the temperature, they are all the same throughout. So we say that after going through the process, the system is still under quasi-equilibrium. Okay? Process diagrams plotted by employing thermodynamics properties, coordinates. Okay? Now, employing thermodynamics properties, we call them as property diagrams. Just like, for example, earlier when you look at this diagram here, this we call a property diagram, which consists of the properties of thermodynamics. So you can have pressure, you can have volume, you can have enthalpy, you can have entropy. You can have enthalpy, you can have internal energy. That will give you what we call property diagrams. Okay, some common properties that are used as coordinates, for example, temperature, pressure, volume. So you might have temperature, entropy diagram, you might have pressure, volume diagram, you might have enthalpy, internal energy diagram, or enthalpy, entropy diagram. Those are all known as property diagrams. Okay, now you have done it, so this is some sort like a revision. It's just a revision for you all to catch up whatever you all have forgotten. Okay, the prefix iso, let's say we say isobaric. Isobaric is constant pressure. So whenever you use the prefix iso in front of, let's say, to represent something is constant, iso is actually referring to some of the properties, some properties which are constants. Okay, let's say, for example, when you refers to isobaric means constant pressure. When you refers to isothermal means it's constant temperature. When you refers to isochoric means it's constant volume. So that is why certain properties they make use of the word iso here to represent that the particular properties is a constant when it undergoes, even though after it undergone a process. So isothermal actually refers to constant temperature. Isobaric is constant pressure. Isochoric or isometric, so usually we call isochoric, or usually we just use the word constant volume. Okay, so that represents constant volume. Cycle. What is a cycle? A process during which the initial and the final states are identical. So let's say, for example, when it refers to a cycle, when the system has already undergone a process, make sure that if, let's say, the initial point, let's say, has a pressure P1 and V1, then the final point has a pressure of, let's say, P4, V4. If P1, V1, and P4, V4, and T4, or P1, V1, T1, and P4, V4, T4, if the pressure, volume, temperature between the first point and the last point, that means the initial point and the last point, if they are the same, okay, then we say it is a cycle. And then a cycle usually consists of more than two process. Okay, more than two process. Okay, so this is an example of a pressure volume diagram. This is an example of pressure volume diagram. So they have defined the initial point and also defined the final point. So the line that we draw connecting, the line that is connecting point 1 to point 2 here is called a process path. And then there should be, okay, you should be seeing an arrow. So whenever you draw a property diagram, okay, remember to put in the arrow that shows that, okay, the process is moving from 1 to 2 or 2 to 1. Okay, so in this case here, we have a property diagram that is pressure and volume. They make use of the properties of thermodynamics pressure and the thermodynamics volume, okay, to be the y-axis and the x-axis, okay. So therefore, we call this as a property diagrams. So, and based on point 1, as you can see, there is a volume V1. And point 2, there is a volume V2. So if, let's say, for example, you refers to a piston and a cylinder device for this, the piston is actually moving from point 1 to point 2. Means that the system is undergoing a compression process. A compression process. Okay, so the arrow is very important. If the arrow is showing in this direction, which is from point 1 to point 2, means it is a decrease in volume, means it is a compression process. But then if your arrow is showing from 2 to 1, that means that is an increase in volume. 2 to 1 means it is an increase in volume if you have an arrow pointing downwards. But then the process becomes an expansion process. So it's very difficult for you, it's very important for you to put in the arrow. That is to show whether it's an expansion process or a compression process, a heating process or a cooling process. Okay. So we have density. So most of you know by now, okay, what is density? Density simply is defined as mass over volume, that is in kg as kg over meter cube, as kg over meter cube. And what is specific volume? This is density, mass over volume. Specific volume is volume over mass. This is mass over volume. But then if you take volume over mass, that will be specific volume. So even sometimes we can also say it is a reciprocal of density. So that means it's 1 over density. Or density, we can say is a reciprocal of specific volume. So density can also be 1 over specific volume. Or specific volume is equals to 1 over density. Okay. So what's specific gravity? Now the ratio of density of a substance to the density of some standard substance. If let's say, for example, you take the standard substance as water. So let's say, for example, you have, okay, blood density is 1.05 kg over meter cube, and water density, 1050 kg over meter cube. And let's say water is 1000 kg over meter cube. Okay, so if you take density of blood divided by density of water, that will give you what we call specific gravity. So most of the time is taken to the reference of the density of water. So anything divided by density of any substance divided by the density of water will give you something which we call specific gravity. And let's say, for example, when you refers to specific gravity of water is 1.0, that means the density is 1000. Okay, specific gravity of blood is 1.05. So a specific gravity. So the density would be 1050 kg over meter cube. Seawater is 1.025. So the density of seawater should be 1025 kg per meter cube. Gasoline is 0.7 specific gravity, has no units, yeah? Specific gravity has no units. Okay, so what will be the density of gasoline? That is 700 kg per meter cube. So that means anything here you times or multiply by 1000, you get the density of that particular substance. So for gasoline, 700. For ethyl alcohol is 790. Mercury, 13,600. Wood is varying from 300 to 900 kg per meter cube. Gold is 19,200 kg per meter cube. Okay, so bones is 1,007 to 2,000 kg meter cube. Ice is 0.92. Air is 0.0013 specific gravity, or density of how much? 1.3. So whenever you multiply this by 1000, you get the density of that particular substance. Okay, so any specific gravity that is less than 1. So let's say, for example, gasoline, ethyl alcohol, wood, okay, and then you have ice and air. Usually they float on the surface of the water. They float on the surface of water. Anything that has a specific gravity of less than 1. Anything that has a specific gravity of more than 1, usually it sinks under the water. Okay? So that is specific gravity. So you take the density of the substance divided by the density of water. And then what is specific wave? Okay, specific wave is given as density times gravity. Gravity is 9.81 meter per second squared. So you get Newton per meter cube. That will give you another term which we call specific wave. Okay, so that is the first part. That is the first part. So we will try to go try to finish as many parts as we can today. Okay.